Let's take a look at the situation. You've taken your telescope out to look at the moon, but you realize you forgot your eyepiece. Don't you hate it when that happens? But you can still get some angular magnification by putting your eye close to the image. Okay, now let's take a look and see how this works. So you're using your telescope to make an image of the moon. So we're going to draw some diagrams that mirror the types of diagrams we see in the book. Okay? Rays of light come into the lens, like so. Image of the moon forms, and it forms at the focal point of the lens. We know that's true. Okay, so the image of the moon forms at the focal point. The image has a height h, and so if we define the angular size here of the image, the angular size of the image is equal to h over f. And we're using the small angle approximation that we use quite a bit in this particular chapter. Now you look at this with your eye, okay? Now your eye is a distance d, okay, from the image, and that's fixed by your near point distance. The angular size that you perceive is this, okay? Let's call that theta sub e. The angular size that you perceive is just equal to the same height, h, over the distance d. And since d is smaller than f, you can see this angular size is bigger. Now, by the way, I haven't worried about plus and minus and things like that. We know the image is inverted. We know that you will see an inverted image. So let's not worry about that. But what we're interested in is the angular magnification. Now, the angular magnification, okay, is just equal to the magnification, the angular size as seen by your eye, divided by the angular size of the image, okay? That would be the magnification that we're looking for. And this is all by way of preparation, okay? And now we're ready to solve. And what we get is this. Magnification is equal to the angular size as seen by your eye divided by the angular size of the image. Well, the angular size as seen by your eye is h, the height of the image, divided by d. The angular size of the image is h, the height of the image, divided by f, the focal length of the objective. Now, you can see the object from 25 centimeters away. So let's go ahead and put in some numbers. D, that's the near point of your eye. That's where you put the image to look at it, is 25 centimeters. F, the focal length of the lens, is 1 meter, but I'm going to write it as 100 centimeters, and so I've got centimeters over centimeters, and everything is going to cancel. Now notice something else cancels here. H goes out. We don't actually need to know the height of the image. What I'm left with is, I'm going to take this equation and rewrite it. It's just equal to 100 centimeters divided by 25 centimeters. And so I got a magnification of 4. Okay, the angular size is 4 times bigger than it would appear if I just looked at it directly. And that makes some sense. That makes some sense if we assess this, okay? The image forms 1 meter away from the lens, and I'm looking at it at a distance of 25 centimeters. And so the angular size is bigger, we would expect, by about a factor of 4. That's, in fact, exactly what we calculate. So, in fact, you can do this. You can do this. It does work. And this assessment is that it matches our expectations of the way the world works.